This video will be going through linear regression using gradient descent. I will be running through how to write the code from scratch in Python, as well as the algorithms and concepts. I will be referring to the Coursera machine learning course, and when going through any machine learning content, it is very important to write the formulas down. You will see a lot of graphs, equations, and notations. For linear regression and other algorithms as well, there's really about 3 to 4 main equations that you need to know to get started with writing the code. So I'm starting this video off assuming that you have some idea of linear regression with gradient descent. Either you finished week 1 of this course or you've done another set of videos or tutorials that such that you understand gradient descent, the cost function, and how to tune the parameters. But I'll just briefly go through it. The whole idea of linear regression with gradient descent is that you are trying to minimize the cost. And what the cost means is the difference between the hypothesis and the real value. When I look at this graph, the hypothesis is whatever the y value is on the blue line, because that is the line that we're trying to generate in this program. We have a set of data and we're trying to essentially draw the line of best fit. So the hypothesis will be the y value that is on the blue line at a certain x, and the actual value is denoted by the red x. As we are writing this program, we have to keep in mind that we want to run this program until our cost is at its minimum. So what we can kind of think is that, the cost should be decreasing as you go down. Once it's at its minimum, if the cost increases, that means that we have reached our minimum. That will be something that we have to keep in mind when we're writing the loop for this program, is that whenever the cost increases, that means the previous iteration is the minimum. And the theta 0 and theta 1 at that minimum should be the parameters that we use for the line of best fit. In other words, we're accepting that theta 0 and theta 1 as the correct slope and y-intercept. So let's take a look at the cost function. The cost function is this formula right here, 1 over 2m times, and then the symbol is called sigma. So this is essentially saying summation of the hypothesis minus y squared. So for every single data point in our data set, we're trying to find the difference between the actual value and the prediction, square it, and then take the whole sum and then multiply that by 1 over 2m. And again, m is the total number of training examples. So in this graph here, there would be 6 training examples because there is 6 red x's. The first thing we should do is just start by creating a function to calculate cost. And hypothesis function, again, since this is linear regression with one variable, the hypothesis function is just y equals mx plus b. Our prediction is this, and then this is the actual value. Let's start by just doing that. Well, I have defined this function, calculate cost, and I'm passing in as the parameters the slope, the y-intercept, and data. So the whole idea is that because we are going to be iterating this algorithm so many times, the we will be calculating cost multiple times, right? So let's say we initially have a slope of 0 and a y-intercept of 0, and then we find that the cost is very high. Then we'll tune those slightly. And then, now let's say it's a slightly different numbers, and then we calculate cost again. It's slightly lower than the cost was before, but it's still very high. So then we're going to keep calculating cost. So for that reason, we should have the slope and the intercept as parameters. And data is just the data set. So for now, I just have 4 data points. So when we run this program and we finish it, we should have a line that is equal to y equals mx, or y equals x plus 0. So just y equals x, right? Because in this case, the slope would be 0 and the y-intercept would be 0 as well. So, or the slope would be 1 and the y-intercept would be 0. In this case, I'm setting a variable total cost, looping through my data set, and then again, the hypothesis function, because we are doing linear regression, the hypothesis is going to be y equals mx plus b. So is linear regression with one variable. Um, Now we are looping through our data set, getting the hypothesis, so that's slope times x0, so it's getting the x variable from here, plus the intercept. So again, this is whatever is passed in. And then just following the formula that we have set out right here. That is the first part. We calculate cost. The second part is that we have to keep tuning our theta 0 and theta 1. So theta 0 is the y-intercept, theta 1 is the slope. And it says here we repeat until convergence. So essentially we repeat this process of tuning theta 0 and theta 1 until we have our cost at its minimum. Once again, there's a lot of information going around, but there's only a few algorithms that you really need to know. Let's create a function now to calculate theta 0, and I have that right here. Like I'm doing before, I'm just following the formula. We have slope equals slope minus learning rate. This is the learning rate times 1 over m times the summation of hypothesis minus y times x. So the learning rate in linear regression is something that you can kind of change. I have set it to a very small number, but I will change it to this. Eventually, you'll see that we should tune this depending on what the results that we get. We have our function here, calculate slope. We also need to pass in data as a parameter. Like we started with the cost function, we are just following the formula listed. Theta 1, which is slope, equals the existing theta 1 minus all of this. We start by first calculating the hypothesis. The hypothesis, like before, is just y equals mx plus b. So we're taking the slope, the current slope, and the current y-intercept, and then here we are calculating the hypothesis. This is all in a for loop because we have a summation here, which is saying perform this action for all of the data, for all of the training data that we have. And you'll notice a slight difference that this is not squared like the cost function is. And we're multiplying x at the end of this. So I have incorporated that into the next line. Difference equals hypothesis minus x1. So that is this part right here. Hypothesis minus actual y. And we have hypothesis minus x square bracket 1, which is pulling the actual y value from these slots every loop, and then multiplying that by the 0th index, which is the x value, which is this part right there. Now we're just performing total cost equals total cost plus difference, taking the whole sum, and then now this is the part where I would actually create a global variable for your learning rate so that you don't have to plug it in like this. For now, I've just done that, but when you're writing the code, I would have a separate variable for the learning rate. You could even pass that in as a parameter. And this is multiplying by 1 over length of data, which is this part right here. So learning rate times 1 over m. And again, m is just the number of training examples. After that, we just need to take the existing slope and then subtract it by that whole part here, which we calculated. And that is what's going on here, is slope equals slope minus total cost. And then we're just returning slope. The next part of this is creating a function to calculate the y-intercept. The equation is listed right here, and you will see that it's very similar to what we did to calculate slope, except we do not multiply the x. For that reason, I will just be copying this code. Pretty much the same setup. The only difference from what we did in calculating slope is that we do not multiply x0 right here, right? We just need to follow the formula and do exactly what it says. We are now returning the y-intercept. Again, I've changed the learning rate, but I will initially set it to this number. And this is kind of a good number to start with, 0.0001. From there, depending on the results that you see, we can adjust this. But overall, same thing going on. We have the cost looping through our data set, calculating the hypothesis, calculating the difference, adding to the total cost, and now updating our y-intercept. So overall, we have the cost function here, which is calculating cost, and we have these functions here, slope and y-intercept, which are adjusting the slope and the y-intercept as we are calculating cost, such that eventually we will find the slope and the y-intercept that fit the data the best. Now the next part of this is just that we need to create kind of the brains of this program. We have the functions. We need to create the part where we are calculating the cost, seeing how much it's decreasing, and when it gets to its minimum. As we will see, this is a complex process, and I'll go through the steps that you need to generate a loop that will get you the most optimal slope and y-intercept. Let's start with creating a larger data set. Right now we only have 4 data points, and that might be too little. So this is machine learning, and just like any person who learns, the more data the better. In this case, we may not get great results because we only have 4 data points. So let's create the data set using a loop. In this case, I have a list of tuples. Each tuple represents a coordinate. This is the x coordinate, this is the y coordinate. Now we have about 111 data points, and if we need more, we can add more later. But this is a better way of creating the data set. We now want to reference this graph to write the rest of this program. The main objective is that we want to calculate the cost and tune our slope and y-intercept up till the point where the cost gets to its minimum. If we were to think about this in coding terms, we want to say that while the previous cost is greater than the current cost, then we'll continue iterating this algorithm and calculating the cost and the values of theta 0 and theta 1. However, once previous cost is less than the current cost, then we want to stop and then accept the slope and the y-intercept at that point at the previous cost as the correct parameters. Because the only time you can get to a minimum is when the previous cost is less than the current cost, meaning that you've got to the minimum and then the cost increased. And if the cost has increased, then you have reached your minimum and you should stop. Let us start writing this code. Initially, when you have not calculated cost and it's your first iteration of the algorithm, default you should set the slope and the y-intercept to 0. So let us start by calculating the cost with a slope of 0 and a y-intercept of 0. I'm also passing in data, as those are the 3 parameters that are needed. So with a slope of 0 and a y-intercept of 0, on the data set that we have, the cost is 2,225.83. Now let's write a loop so that we can continue to run this algorithm and adjust the slope and the y-intercept until we've got to our minimum. In here, we also want to tune our parameters. So we will be calling the functions that calculate slope and calculate the y-intercept on each iteration. If you're following along with my code, keep in mind that I have changed this function's name from intercept to calculate intercept. So we need to adjust this because we need to define previous cost. Because for the first iteration of the algorithm, we want to define cost and define previous cost so that the loop will enter the loop on the first iteration. Because of that, I will just initially set previous cost equal to cost plus 1 inside the loop. Inside the loop, I will do this so that now I'm setting previous cost equal to the cost and then cost equal to the next calculation of the cost so that we can keep this cycle of having the previous cost equal to the previous cost and then the cost equal to the current cost. And then we're able to keep this loop going. So let's print cost and then see what happens. We are seeing that the cost or the loop keeps running and the cost keeps printing. I'll explain why, but before we alter this code, let's print the cost and the slope and the y-intercept so that we can see what the numbers are approaching. We can see that the numbers are approaching the correct values. For example, the slope is approaching 1, which is correct, and the y-intercept is approaching 0. But we are never, the program is never declaring convergence, or this loop is never stopping. And the reason is because of calculus. What's happening is that you can always go infinitely smaller. You can go smaller and smaller and smaller. So what's happening is that it's never getting to the point where it's at its absolute minimum, because it's just going infinitely smaller every single time. And what I have done is I have Googled when to declare convergence in linear regression. We can see one here that says, in practice, we declare convergence if the cost, j of theta, decreases less than 10 to the negative 3 power. In other words, if the previous cost has decreased 0.001, less than 0.0001 to the current cost, then we can declare convergence. I would say that this number is arbitrary. First, try to see the results, how accurate your program is, and then maybe try different numbers, just as you do with the learning rate. But let's try that number. So we are saying we will continue this loop while the previous cost is greater than the current cost, and the difference between the previous cost and the cost is greater than 0.001. In other words, if it's less than this number, then this loop will break. So let's put this on the outside. So we can see that now it has declared convergence at a slope of 0.9999477 and a y-intercept of 0.008067. The numbers are very, very, very close, but not exactly correct. This is the situation I was talking about where you should try tuning your parameters and seeing what the results are, or tuning with the numbers in general. So in this case, it is difficult to get exact numbers. Obviously, in something like this, maybe you round your numbers up. So the slope would be 1, the y-intercept would be 0. I would also try maybe adding more data points to your data set and see what the results are. So with a 440 data points, we see that the slope is totally off and the y-intercept is also off. I would do two things. One, maybe adjust this number here, which is calculating when to declare convergence. It's probably too high in this case. So now we can see that the slope is back very close to 1 and y-intercept is very close to 0 again. And this is just tuning the number which we have declared for convergence, and also adjusting the learning rate, making both of them even smaller such that it's taking smaller steps in the learning rate, and also it is taking more iterations of calculating cost. Now let's say I add 700. We can see that the slope is still pretty much the same, and the y-intercept again is now negative. And now again we can see that with more data, the slope is again very off and the y-intercept is very off. That is why I say the numbers are arbitrary, is because you have to see your results and then decide what an appropriate learning rate is, and what an appropriate number is to declare convergence. Now again, we are back to the same numbers we had before. And because this is a data set of the same coordinates for x and y, let me print the data set again. Because this data set has the same values for x and y, the equation that we expect to get when we run this program is that the slope is 1 and the y-intercept is 0. As you were going on, I would continue to change the parameters and try it on different data sets of different sizes and different types of data so that you understand how to tune these parameters. This gets very into the math and understanding the theory behind machine learning. And I would do this for all the algorithms that you encounter. A quick note is once you have finished this video and you have implemented linear regression in the same way or even a slightly different way, be sure to post it to this website, nexclap.com. It is a STEM portfolio tool where you can essentially build your STEM portfolio. You will see different categories of STEM and a lot of machine learning content. You can post your own way of doing it and also see how other people implemented any AI related content, whether it is linear regression, logistic regression, or neural networks. There is also online courses. The one I'm showing you is Python Level 1A. This is in the online courses tab. There will be more courses added in the future.